So, as Rob said here, my name is Thom CherryHomes. I'm with the FujiNet project, but this talk has absolutely nothing to do with FujiNet. That will be Mark's talk today, but that will end. I'll be talking about it tomorrow, and we'll be doing FujiNet stuff in the classroom. So if you really want to see what FujiNet's all about, please come by the classroom and watch it in action. So, but my talk today here is actually about game development and how game development was done back in the day. Initially, this talk was going to cover how you would use systems like S100-based systems to do game development for Atari 2600 and Atari 5200 titles. But as luck would have it, Al Caso tapped me on the shoulder one day, and he pointed me to a disk that had Atari's coin-op assembler, linker, and associated tools backed up on it. And so I took the task of basically resurrecting that, making it run on RT11 in SimH, and I'm going to show the process now of going through the process of taking that assembler, using it to modify a piece of source code. In this case, it's going to be Centipede, the coin-op version of Centipede. We're going to assemble the results, we're going to link the results, and we're going to see everything in action, but you'll get to see everything in context. So, a bit about Centipede itself. Centipede was a coin-op operated game, first released in early 1980. It went through several revisions. The revision that we're actually going to be dealing with here is revision 2 that was released on May 28th of 81. It has a 6502 CPU. It has stamps for players and enemies, and it's got a background layer for mushrooms, the title, the scores, everything else. The graphics hardware is 2 bits per pixel, 4 colors for each playfield and each stamp. And for those who need to see, that's the Centipede cabinet right there in all its glory, with the trackball and everything. A great game. If you've never played it, it's worth playing, absolutely. We're also going to see, this is a screenshot of the game right here. We can see the individual tiles for text here, the stamps for the mushrooms, and the stamps for the player here, and the enemies and the various enemies and whatnot. But for each of these games, you had a bespoke computer that was basically built for them. The hardware for each game was made specifically for each game. And even though for a lot of games in the same time period, they would use similar hardware building blocks, the board for each game was unique and different. And what we're actually going to be doing here in this case, we're going to be modifying program code to go on these 2K EPROMs down here at the bottom of the board, and we're going to be modifying and placing in the picture data to go in these 2K EPROMs here in the middle of the board. There's also a sync EPROM that basically functions as a finite state machine for various internal functions of the machine that we have to build as part of the build process too. So, the machine that we're going to be simulating here is the machine that Atari had in coin-op for their first bits of microprocessor development. It's a PDP-1120. This was a mini computer that was built by Digital Equipment Corporation, announced in 1970, shipped at the end of 1970. This is a particularly beefed out PDP-1120 here. We've got a couple of TU-58 tape drives on the top. We have a paper tape reader here in the middle, the front panel here with the main parts of the machine here, right in this panel here, and some ancillary bits underneath. And the primary input for these machines ranged from anywhere from these teletype Model 3 33 ASRs to VT05s to VT52s, VT100s, and the like. The peripheral complement that we're going to be using here is a machine with roughly 32 kilowords of memory, which is just enough to comfortably run a copy of RT11, which we're going to be using as our operating system in this case. We're also going to have 3 of these RK05 2.5 megabyte cartridge disk pack drives. Each of these holding, the first pack holding the system, the second pack holding our source code, and the third pack essentially having our binary artifacts. We also have, for backup purposes here, a DEC RX01 8-inch floppy disk. This basically emitted standard IBM 3740 format floppies at 256K apiece. And for output, we need to be able to take the output that we have here and run it over to our EPROM burning station. And that's going to take paper tape. So we have here a PCO5 that's literally going to be outputting our artifacts here. And we're going to ferry that over from paper tape to our EPROM burning station to split up our EPROMs to put in the machine. Now, the one thing that they didn't have at Atari was a VT100, but we're going to be using a VT100 as our terminal here, so it's nicer than what they had there. Initially, they just had a Model 33 teletype that they were just using there, and they were using TICO, which if any of you guys have ever seen TICO, the command structure in TICO looks like line noise. But it's a very powerful editor. We're going to be taking a few steps up from that. I don't want to subject you guys to TICO, so we're going to be using the keypad editor, KED, which is a full screen editor which runs on this VT100, which is the reason why we have it here. And for the operating system, they started with a copy of RT11 version 2, then they quickly went to version 3, and by the end of 1980, they were running on version 4. So we're going to be using version 4 here because it has KED. So essentially, what we're going to be doing here, once we have everything built, we're going to take it over to our simulated black box system. Atari had specialized hardware for stepping through and debugging their software. It was a combination of their output boards, and they had support circuitry so that they could take and step through instructions, look at set breakpoints, figure where things were going wrong, and it just working from that point. But they also used logic analyzers, like the HP 1611A, very indispensable for doing instruction traces, for just for checking, for doing the low-level debugging that was often needed too. And we're using the paper tape here because we're using it as an example of some of the improvisation that they needed to do to get things moved from one system to another, because they had to take and cobble these things together with what they had in the lab, because you couldn't just, there was no off-the-shelf anything, especially in the earliest days of microprocessor-driven game development. Everything had to be built in-house. And unfortunately, much of that hardware doesn't survive today. But we're trying to take and show I'm trying to take and show the process with as much context as I can, filling in the blanks where I need to. So the first thing we need to do, we're going to be taking and modifying a piece of Centipede source code. To do this, we need to be able to edit the source code. So we're going to take and boot into RT11. We're going to use the text editor to take and make the requisite change. And we're going to take and we're going to go ahead and we're just going to do that. So let me take and bring up one of my other windows here. Thanks to the magic of SimH here, we can take and run this complete PDP-11 with RT11 and all the software here. And the nice thing here, in the references section at the end of my talk is a link to the GitHub so that you can take and look at all of this software and run this software on your own environments as well. So we've booted up our virtual PDP 1120 here. We're in RT11 and we are using the SJ variant. Everything's set up so that we can use it here. And this is basically the default text that comes up for the distribution. Haven't changed it. This would be something else. But if we do a directory on our main system drive here, it's a very basic RT11 installation. with a few extra files that we have here on our system drive. We have Mac68, Mac65, and LinkM. The Mac assemblers here, and this is really the cool thing, the way that they implemented 6502 cross-assembly at Atari CoinOp was that they literally took Macro 11 and they transmogrified it to spit out 6502 code, to spit out 6800 and 6809 code. It's one step away from crazy. And they built a special version of Link to take and output 8-bit code and to do all of the mappings and the listings and everything in hex instead of octal. So the first thing we're going to do, we'll take a look here. Excuse me. We'll look real quick on DK1. Our source code is sitting here on DK1. Let me go ahead and do a quick assignment here so I can set the default drive to our disk here to make things just a bit easier. And we will take and invoke KED with the edit command. We'll take and modify CentIR2 Mac. And here is basically the second segment of the Centipede source code. In this case, the first part of this source code is what we're after here. We're going to take and do a quick little change of the message here. We're going to change this right here to Hello World. And then, because I'm using my laptop here, and my laptop does not have a VT100 keypad, I have to take and simulate the command keys to take and finish my edit process. So I have to take and start with entering keypad 7, which puts us in command mode. OW, which, whoops, come on, there we go. No. Short answer, no. We're going to go ahead, we're in command mode now, and we will exit, which will save our changes that we've just done. But I can't hit the return key. No, I have to hit the keypad enter key. So another escape sequence. It saves the file. We're back in RT11. Everything's nice and done. Okay. So at this point, we've taken Centipede source code. We've done a modification to that source code. Now we need to take and assemble that source code. To do that, we need to use, on our system drive, we need to use Mac65 down here at the bottom here, because this is 6502 assembly code, and we need to create our object code. But you can't just type Mac65. This is RT11. It's a save file. We have to use the R command or the run command to run it. We are now inside of Macro 65. It works exactly the same as Macro 11. If you've used pip under CPM, this is where pip got all of its mannerisms from, quite literally. From pip in RT11, from pip in all of Digital's operating systems, as a matter of fact. In this case, we need to enter in a special syntax called CSI, which is just a fancy way of saying you need to give the destination file name equal to the source file name that you're going to build. We need to take and build each individual piece. What are we going to build? Well, if I take a look real quick on DK1, we need to take and build Centi2, CentIR2, CentTS2, CentPic, and the sync file. The CendDef and the Coin65 files are included by the Centipede source code, so we do not have to take and assemble those explicitly. So we'll go ahead and run Mac65, come back in, and we'll start with the Centi2 main source code. I'm asking it to create a Centi2 object file from centi2.mac. I do not need to put in the extension. Thankfully, because we're running on simulated hardware, I do not have to run this at the actual speed that this would happen on a real system. On a real system, this assembly process, the whole assembly process, would take about 20 minutes. I don't want to waste your time. So we'll go ahead. We've assembled the first piece here. No errors detected, and we've got roughly about 2 kilowords of core left. It's a good thing that we've got 32 kilowords of core in this machine, because it's just barely big enough to take and do the assembly. We do the same for CentIR2. We do the same for CentTS2. We do the same thing for CentPIC. And we build the EPROM. For those of you that are wondering what's happening here, I had to press backspace a couple of times. RT11 needs to run on a wide variety of terminals, including Model 33 teletypes, which means that when you do a rub out, it needs to take and print that rub out in a way that makes sense for teletypes, which means I'm going to print the character I just deleted with the backsplash character in front of it to indicate that that's where the delete cursor is. Yeah, you can interrupt at any time, please. Yeah, go ahead.
Anyway, real quick, what's the word length in this P11?
It's a 16-bit word length, 18-bit address space.
Ah, okay.
Okay. Yeah. So, now that we've taken and assembled all the pieces, we're done with the assembler. We can hit Control-C to finish up. And if we do a directory at this point, we see that we've created a handful of object files. These object files are not complete, though. And the reason they're not complete is because the assembler has taken and generated code that is relative. Everything is relative to the object file itself. And what needs to happen now is that these files need to have all of those addresses resolved to absolute addresses on the 6502 address space. This is important because the 6502 cannot do relative code at all, position-independent code at all. So we're going to use a linker, or actually more accurately in this case, it's a loader, but they call it a linker here, to take and put these files, to resolve all of those relative addresses, turn them into absolute addresses, and wind up with a binary file image that we can take and subsequently split up. So to do that, we're going to use another tool here on the system disk called LinkM. Why LinkM? It's the linker for microcomputers. This was another custom tool that Atari built inside CoinOp based on the Link 11 source code that you could get from DEC, just like you could get the Macro 11 source code from DEC and modify it for your needs. So go ahead and run LinkM. Wait, another asterisk prompt. Does that mean we can use a CSI syntax here too? Yeah, pretty close. And for that, we need to take and specify the same thing, destinations. In this case, we've got two destinations that we're going to take and build. The first is the object file, and the second is the map file, which has all of the resolved addresses that the linker went through and fixed up in a nice little file, printed file that you can take and reference. And we'll look at that map file in just a moment. But we need to go ahead, take these three object files that we built as part of the macro process here, bring them all together into one Centi2 output file along with the map file. No errors in the link, nothing went wrong, so it simply just drops us back to the CSI. Do the same thing for Synpic, and we need to build the sync prom too. Always fun. I don't usually use my touchpad. Okay, so we've built the final binaries here. What did we wind up with? If we go to drive 2, DK2, we see that we have our final binaries here in save format here, and we have our map files. If we take a look at the map files, you'll basically see that we have this map file showing all of the symbols inside of the object that needed to have their addresses fixed up and the addresses that they wound up being assigned to. It's a map. You can see where everything starts, where the high address is, and it's just to make sure that everything gets assembled as it should. Okay. Rub out. No, it's crazy, I know.
So what terminal do you say they usually use? They started with a teletype, with a Model 33 teletype, and then they went to an ADM3A. They never had a VT52 or VT100 at Atari. So I wanted to spare you guys a little bit of the pain here, because if I had to use an ADM3A or a Model 33, I would have had to have used TICO to do all of my edits, and I would have lost 99% of you. So, yeah, it would have looked, yeah, TICO looks like line noise. They had, yeah, and they did have EDT later. So, but EDT is basically TICO with a few things kind of sprinkled on top of it. Yeah, well, yeah. So, now that we've got our artifacts, we need to bring them over to the EPROM station. The EPROM station takes paper tape. The nice thing about the PC05 paper tape here is that it actually can output 8-bit binary data just fine. So we can take and use the paper tape here to take our artifacts and bring them over. To do that, we need to attach a little chunk of paper tape into the paper tape punch. I'll make sure I got, okay. Attach paper, no. This is new, so okay, it created the file for us, and now we can come back into the simulator here. And we can use a shortcut of the pip command, which is one of many weird little shortcuts that RT11 has inside of it, the copy command here. And this is literally where the copy syntax for MS-DOS came from, pretty much verbatim. Yes, DCL, absolutely. So we're going to take and copy. Yes. Oops, sorry. So now we've taken and punched our paper tape for Centi2. We need to do the same thing for Synpic. And we need to do the same thing for our sync prom. Okay, now those files are on paper tape. We'll head over to the paper tape machine to do the rest. I want to take this moment here to take a small aside and show some of the commands that I'd been doing here were actually part of a command file, which is the build script for the system. The reason I didn't use this command file was because I wanted to show you guys the individual commands themselves as they were being run and in context, but also we're missing the one piece of software that they use to basically split up the EPROMs. Thankfully, that's not a very tough job to do, and for its proxy, we'll actually be using DD in its place over on the Unix side. But we'll see that our command file here is essentially the same thing we did before. They set up some assignments. They take and do the assemblies. Then they do the links, like we did there. And then they have the individual image files split up into their EPROM files by part number. These are 2 kilobyte EPROMs. And part of the reason that we have to do this, I'll show you in just a split second, the files that are created by the linker here, especially with the program code, have some empty space up at the top because the address for the Centipede doesn't start at 0. It starts at hex 2000. So there's an 8K gap at the top of the file that has to be chopped out. So now we have those bits and pieces. We can stop the simulator here, and we can continue. We have our individual binary files here. If we take a look at each one, we have 4K worth of picture data, which needs to go into the 2 picture proms in the middle of the board that you saw earlier. We have roughly 16K worth of assembled here that we need to take and split up into the assembly files here. And we have our sync prom. And I'm noticing here that the size of the Centipede file here is slightly off, so this may actually blow up in my face. And if it does, I apologize ahead of time. But we need to go ahead . Yes, that's not present. It wasn't on the disks that we received, so I don't know. It wasn't there with the rest of the tools. I don't know why it's not there. I've been talking with Dave Shepard, and he doesn't have a copy of it either. Dave Shepard was the engineer in charge of the build tools, and basically, he actually has a GitHub full of all sorts of other artifacts that are a bit later than this, from, say, the Marble Madness era and whatnot that ran on the VAX, and and he has all of that stuff in his GitHub here. But we're going to go ahead. I'm going to take a look real quick. If we they used RT11 in CoinOp from 1976 until about 1982 when they replaced it with a VAX. So, and when they replaced it with the VAX, they actually went through and retooled all the tools to, they retooled everything in C. So we can see this is the main Centipede binary itself. And because the loader is literally generating absolute addresses here, there is nothing in the first 8 kilobytes worth of the file. Nothing got mapped here, but it still needed to output that image file because save files are absolute minimum memory images that have to be contiguous. So we scoot down, and we'll start to see, once we get down to 2000 or so, we start to see our EPROM, including the all-important copyright message right here that appears in several places in the ROM. You do not touch this because they do CRC checks on various parts of the ROM, including the copyright message, and if you mess with this and it doesn't match up, the game will deadlock. Yes, you can. But you can change that anyway. Yeah, we have this full source code here, but most of the ROM hackers didn't. So yeah. So anyway, but yes. So we have this here. We have our bits and pieces. Now we're just basically going to take and use DD to generate all of our little cut-ups here. And all it really is, you'll see here that I'm working with each individual save file here, and just like in the command file, outputting them to their EPROM IDs and their physical locations on the board. These last bits here are the grid locations for those EPROMs on the board. And since each of these are 2716 EPROMs, they're 2K apiece, save for the sync PROM, which is 256 bytes. So, with that, we'll go ahead and grab that. Do all of that at once, and DD makes very short work of it here. Got these 2K EPROMs now, and they're now in the place to be used by our black box system here. As I said, I noticed that the file length for the main program code was a little bit different, so hopefully this works. I did a rehearsal on this yesterday, and it was just fine, but my luck has been kind of funky. And yeah. Yes. And yeah, it was the same length. I made sure of it. That's not the, I noticed that even with the loader, with the way that the loader maps everything in, it should be exactly 16,384 bytes. So in lieu of that, can't believe I'm doing this. Sorry, let me go to my, let me actually go to my thing here. I'm going to pull this up from the video and pretend I did it. This was me doing it just a month or so earlier. Come on. Oh, come on, don't do that. You can see I'm going through exactly the same process here, making exactly the same change, doing the assembly, doing the link, bringing everything over. No, again, I noticed that when the link happened, it was a tiny bit too big for some reason, so something wasn't quite right. Looking at the, let me pull this full screen here, and we'll start the game here. I'm starting it with the debugger, and we can see that everything stopped and in reset mode here. And once I actually take and start the debugger here, the game will start running. This is the MAME debugger. It's the, in this case, it's no, it's not the PDP-11 debugger. It is quite literally the MAME, the debugger that's in MAME itself. Oh, the MAME debugger. Yes, quite literally. Yeah. We see the game running right there with our change. And I'm pretending that I did it here. Okay. All right. So that's basically it for my side of the talk here. Thank you guys very much. Do you guys have any questions? Yes.
Are you going to get real hardware and do like the whole thing real?
I wanted to actually do that here for VCF. I couldn't wrangle up somebody who had a Centipede board to take and do the ROMs, but I wanted to do that for here.
That would have been cool.
Yes.
If people do have any questions, then just give me a chance to bring the mic over to people so it gets recorded.
Just because you just mentioned it, what step generates the CRCs?
Sorry?
What step generates the CRCs?
That has to be generated outside with an external tool. They had a little tool for generating CRCs from the binaries, which you would then take and inject into the code manually.
Oh,
And if you actually take and look inside the source code itself, there are various places inside the Centipede source code that you have to take and inject CRC, and they're all separated by section.
So my apologies if I missed part of this, but so when you were developing the software, they were coding it obviously on, you know, mainframe and on MIDI, and how did they sort of debug it and figure out how it all, you know, tracked?
So they basically had to use what they called a black box, which was a piece of custom development hardware that they built at Atari. It would plug into the CPU socket and would intercept all the signals from the CPU socket. We call it an in-circuit emulator today, basically. And you could then take and set breakpoints. You could take and trap on certain conditions, such as interrupts, and and so on. So they would use that, and they would also use, for example, HP 1611A logic analyzers, particularly because the 1611A had instruction histories and full instruction decoding and the like.
That sounds like hard work.
Yeah, very hard work, especially when you consider that for the majority of the early Atari coin-op, they literally had to take and do their code changes on paper, write them down on paper, hand them to a key punch operator, one of two key punch operators, to take and enter the code into the editor. And the key punch operators were actually very smart cookies in and of themselves. They got very adept at finding potential typos in the code and fixing small bugs in the code as assembler errors would pop up. For big assembler errors, they would simply give you the error output, and you would go back, make your changes, figure out what went wrong, and then go through the whole process again. If everything was right, what you got back was a paper tape containing your binary, which you could then take over to the EPROM station to burn your ROMs.
Yeah. Now worry about how hard it is to put breakpoints and laser lights, isn't it?
Understand.
How-
So, since a lot of these games had custom boards, which typically came first, the software or the hardware, or did they work in tandem?
They typically worked in tandem, but the game would have a basic set of specifications. And those basic set of specifications would amount to, okay, what do you need? How many stamps do you need on screen? And when I say stamps, this is a Atari specific term for what we know today as sprites. How many moving stamps do you need on screen? How many background layers do you need? How many bits per pixel do you need to take and have as many colors as you need? And so on and so on. What do you need for sound? And which in the case of Atari usually at that time was, okay, how many pokies do you need?
Yeah.
And so on. And all of that would be drafted down. The hardware guys would be working on the board. You would have a preliminary memory map so that you would know where hardware was inside the system, where you would expect things to be, and you could base all of that information on what was being built to write your program code while the hardware was being brought up. The one thing I didn't bring up here was because it hasn't been found, is the initial art package that they used called Sketch to take and do the graphic drawings for the Centipede characters, the mushrooms, etc. That was a very custom piece of hardware that they threw together very quickly for the express purpose of doing the bitmap graphic stuff to go on picture prompts. And at some point I would love to find it. Yes?
So based on what you just said, is it true then that the hardware that generates the video is different for each machine and was basically logic gates, or were any melosite chips used, or how did that work?
That's and the answer to that question depends on which era of Atari coin-op you're talking about. The early Atari coin-op, yeah, it's all 7400 series logic, and it's all custom for each game. And while you would have certain similar sets of specifications for different games, the video hardware was a little bit different for each individual game. And I'm not even talking about the vector games like Tempest or Lunar Lander, etc. They actually built not only a custom digital vector generator, courtesy of Howard Dillman, they also had the special 2901 based bit-sliced math coprocessor that they called the Math Box. That was used for Battlezone, Star Wars, and so on. That's all vector stuff, though.
Good morning.
Morning.
Oh, sorry about that.
Hi.
Hi, see you all. So, I walked in late, but did you say that you developed this on mainframe?
This was, no, I didn't develop this.
Oh, yeah.
These were tools that were created and used at Atari Coin-Op to develop their games. And for the first time in history now, we can take and use those tools to take and reconstruct the source code that was dropped onto GitHub a few years ago, and literally show the process of building these games from beginning to end and in context with these tools, because the tools have recently been found, in particular the assembler and the linker.
I heard the magic word key punch.
Yeah, key punch operators. They had two of them basically just to do program listings.
Any more questions out there for Thomas? Oh, yeah.
I also came in late. Did you, is the link for the GitHub page? up
Yes,
on the web-
that's all in my references here. If we actually take and go right here onto our references here, we have, there's a link to the GitHub here for everything that you saw in this presentation, including the tools. There's a copy of Centipede version 4 there that can be assembled against. Then there's a link, of course, to SimH, which you will need to be able to run all of these things. The repo contains a configuration file which sets up a PDP 1120 with all the bits and pieces that you need. And you need the Atari Coin-Op tools. The Atari Coin-Op tools were placed, once they were all resurrected, they're all now on bit savers here, and they're in this zip file here if you want to get them individually. And of course, there is the incredible historical source archive on GitHub, which has source code not only for games like Atari Coin-Op games, but for every game that Infocom released, and so on and so on. It's historical source that's being preserved by Jason Scott and his team. Yes.
So, one sec, let me get my team.
Yeah, I asked a previous question, and you mentioned slightly later in time you were using VAX and rewrote everything in C. Is that also available on GitHub?
That-
All the C code that was used
As
on
far
the
as
VAX for next gen?
Now, Dave Shepard actually has a GitHub with as much of that stuff as he has been able to find.
Okay, so he has bits and pieces that may
Yes.
or may not be
Yes.
sort of complete.
Yes.
Cool.
One more.
Are the hardware schematics available anywhere for the games?
That's a good question, and I'm not exactly 100% sure on that. You can, of course, I mean, that's kind of a loaded question, because many of the field service manuals provide complete schematics for the games too. So from a purely hardware perspective, yeah, you've got complete hardware schematics that way. As far as the schematics that were drawn internally at Atari, don't know where those are. Yes.
Coming back to that CLC check you mentioned,
Yes,
why are you getting away with making changes and not updating that?
because the CRC changes only are for specific things such as the copyright string. Which is the first thing that the pirates would change.
Do you have any insight into like the time frame of the development process of, let's say, Centipede?
Can you be more specific?
Like, so from, conception to actually successfully.
That has been covered many times over by both Donna Bailey and Ed Log, and it's not really my place to tell any of that. I'm trying to bring something new to the table.
Okay, gents, are you done?
I apologize for that little hiccup at the end. I did a rehearsal of this last night and that didn't happen, so. Oh well.
Yep, so thanks everyone for coming on and listening to Thomas. That's been very informative and great fun. We'll be reconvening here in about 10 minutes where Mark Fisher will be doing a slightly related talk on FujiNet development. Thank you.